because it's Erwin Shapiro's birthday.
Oh.
And of all the birthdays, this one is notable because Erwin is now 90 years old. So he's added one more accomplishment to his long list of accomplishments. And so we could say congratulations and happy birthday, Erwin.
Happy birthday.
Happy birthday to you. Happy birthday to you. Happy birthday, dear Erwin. Happy birthday to you.
Thank you very much. And I still play tennis.
Erwin, you look 40.
Do you need new glasses?
Okay, well, on this particularly joyous Thursday, it gives me a special pleasure to welcome you all to Professor Rachel Somerville's ITC Colloquium. So Rachel will be very well known to everyone here, I'm sure. She did her PhD in Santa Cruz and then went on to the Hebrew University and Cambridge in England for postdoctoral stints, and then a plethora of professorial positions ranging from Michigan to Heidelberg to Space Telescope to Rutgers, where she was the department chair in astrophysics.
No. I just held an endowed chair. Very different.
Right, okay. I don't
One you want to run from, the other one is...
I don't understand
okay.
these distinctions in the United States. Anyway, it doesn't matter. So, but she is now full-time at the CCA, where she is the leader of the Galaxy Formation Group. And Rachel's work has certainly not gone unnoticed. In 2013, she won the Danny Heinemann Prize, recognizing her contributions to the field of galaxy formation, specifically in the use of semianalytic model simulations and combining all of that with observations. And as of 2014, she's also a Simons investigator. So without further delay or anything that I have to say, I'll let Rachel carry forward.
Thank you so much for that introduction, and thank you very much for inviting me here. It's been a while since I visited the CFA, and it's great to see some familiar faces as well as to meet some new people on this 2-day visit. Although it looks like the weather is trying to make me feel like I'm back in the other Cambridge, but that's all right. I wanted to say, by the way, as with many people at my career stage, none of the work that I'm going to tell you about could have been done without my amazing collaborators and the postdocs and graduate students and undergraduate students that I work with. If I listed them all, it would sort of take up a whole slide. So I've decided instead to try to put the relevant names on individual slides presenting the individual results along with pictures where possible. So what is our project? What is our impossible dream? Our dream is to be able to simulate and understand how we got from the relatively simple initial conditions that we see imprinted on the cosmic microwave background to the amazingly complex and diverse galaxy population that we see around us in the local and distant universe. And I think this is perhaps an appropriate place to give a shout out to Jim Peebles, who's a personal hero of mine, and I think probably like me, many of the people in this room learned cosmology from his textbooks. So I was very, very pleased with the news this week. None of the work I'm going to present today, I think, would have also been possible without the foundation that Jim and others of his generation laid down for us. Now we pretty much know the initial conditions. We pretty much know how much dark matter, how much dark energy is there in the universe. And so we just need to work out what happened over the last 13.7 billion years. And not only do we need to understand and explain, account for, aha! Hi, Avi. Good to see you. You'll be able to keep a close eye on me from there. Tell me if I make any mistakes. Not only do we need to be able to account for this diversity in galaxy internal structure and morphology that we see from dwarf galaxies to grand design spirals to giant elliptical galaxies. But we also need to account for the fact that they seem to know where they should live in this very large scale structure that's laid down by those cosmological initial conditions, right? So we know that galaxies seem to have their internal properties very much correlated with their larger scale environment. So how does that come about? So, we have a broad brush picture. You all know this sort of broad brush explanation that structures, gravitationally bound structures, form through gravitational instability in the expanding universe. Presumably as the dark matter accretes into these halos and becomes bound, also gas accretes into those halos where it can cool into galaxies and form stars. Stars explode as supernovae and also deposit radiation and winds in the interstellar medium, thereby causing what we call stellar feedback. And also black holes can form in the centers of galaxies and accrete and then also deposit radiation, winds, jets, etc. So this is galaxy evolution in 30 seconds. But there are a number of puzzles that I think remain open for us to explain. One is that we see these scaling relations between global properties of galaxies. Things like stellar mass-halo mass relation, the black hole mass-bulge mass relation, the mass metallicity relation. So how is it that processes occurring on these very local scales, near the sphere of influence of a black hole, for example, or an individual supernova, can affect these global scales of galaxies? And indeed, which scales are actually driving these scaling relations? So here's an example of a scaling relation. So I showed the global version of this. This is sometimes called the star-forming main sequence, or the star formation main sequence. This is a controversial term. Some people love it, some people hate it. Basically, there's a correlation between the rate that a galaxy forms stars globally and its stellar mass. Here it's plotted as the specific star formation rate, just to be confusing. If you break galaxies down into little pieces, into little spaxels, as we can now do with integral field unit surveys, it turns out that each of those pieces sits on that same relation, that same main sequence, if you like, and the slope is the same as the global relation. So did that global relation arise because pieces of galaxies knew that they were supposed to lie on it? Or, in contrast, there have been papers written suggesting that no, it's actually because the rate that gas flows into halos has that same scaling with the halo mass. So actually this is not coming from the bottom up, this is kind of coming from the top down.
Is the slope equal to the
And the
universe
slope
age?
is also unity.
No,
right?
but is it the age of the universe? Because star formation rate divided by star.
Yes.
The stellar mass gives you an age.
Yes. Well,
Is
of
it
course,
equal to the age of
the
the universe?
normalization of this changes over time.
Because the age of the universe changes.
Yes, and that agrees with what you get just from halo growth, the change over time. That doesn't prove that that's where it comes from, but it does agree numerically with that rate. So, I think that probably the answer is both, that these scales are communicating with each other in complex ways, but this is another example of one of the questions we'd like to address. And why do we need to do this? Why do we need to solve this problem? Well, as you're all aware, we already have quite good imaging of maybe a square degree or so of the sky from Hubble, but that's going to be nothing in the future, right? When we're going to have sub-arc-second imaging from LSST, from WFIRST, of thousands, if not tens of thousands of square degrees of the sky. So we need to get ready to really glean the most possible scientific insights from those observations that will be here before we know it. Okay, so one possible way to make this link between the dark matter distribution that I showed you and the galaxy population is using what are sometimes called semi-empirical methods or abundance matching methods, where you basically, there's no physical model. You just ask, how do I have to put galaxies into halos to match observations? I am not going to talk about those methods in this hour. I will talk about that in my lunch talk. But those are, of course, very important and powerful methods. Another approach, which to me is really in this category of mapping rather than modeling, is to use machine learning methods. I think that this is actually quite an interesting way to go. I mostly won't talk about it, but perhaps at the end, if we have time, I'll tell you a little bit about some of our forays into trying that. But in this talk, I'm more interested in thinking about how we can make a physical model and come to a physical understanding of the processes occurring in galaxies in a cosmological context. So suppose we want to just put all the physics in a computer and solve all the equations and get the answer in perfect detail. That would be great, but unfortunately, as you all know, there are some fundamental limitations that simply come from speed of CPUs, limitations of memory, etc. So this is quite a nice diagram. I hope you can read it from the back. You probably can't. But this is from a paper recently put out by Dylan Nelson and collaborators. So what's shown here is the number of galaxies, the cumulative number of galaxies that are resolved as a function of their mass. So these are sort of cluster masses, these are dwarf galaxy masses.